All righty, good afternoon. Today on this wet and soggy day, again, we will continue our discussion of ionic substitution reaction mechanisms. And I want to say one final thing about what we talked about last time, which was carbocations. Remember, we talked about structure and how they react, etc. There is a tutorial on the website about carbocations. It is the most complete tutorial that's there, and it covers quite a bit of stuff. So if you're having difficulty with carbocations, that may be a useful place to go. Today what I want to do is consider an alternate ionic substitution mechanism, different reaction. And the reaction I want to consider is this one. Let's just put it that way. And if we react that with water, we could get a substitution which looks like that. So I want to talk about the mechanism and so forth of this process, and let's start by asking the mechanism question. Of course, we have to understand mechanism that's going on before we can think about kinetics and how changing the leaving group and so forth might matter. So if we start by looking at this, so far we only know one substitution mechanism. As we go through the course, we'll learn several, but right now we only know one, and that's SN2. So we can ask ourselves, is this a reasonable SN2 reaction, or maybe something else is happening here? What do you think? Is there anything that absolutely forbids and prevents this from being SN2? No, there's nothing that prevents that. Remember, the only thing that's going to absolutely positively prevent SN2 is leaving group of tertiary carbon. Here the leaving group's on secondary carbon. But, or is it? Tertiary carbon, right? Remember pH, benzene ring? There's a carbon here as well. One carbon, two carbons, three carbons. So that's a tertiary carbon, so SN2 absolutely prevented. Yet if I go into the laboratory and take this molecule and add water to it, granted I have to heat it up, but it certainly will react, it'll become then alcohol. So we need to figure out an alternate mechanism. And the alternate mechanism is the one we talked about last time, where the leaving group leaves, we make the carbocation first. So I'm going to write out that whole mechanism, and I'm going to include the transition states, of course, because we need transition states when we're talking about kinetics. So how does this process work? We said this mechanism begins with the ionization of the carbon-leaving group bond, and then we're going to have a transition state with that ionization occurring. So the leaving group, partly gone, methyl back, still attached. Transition state. Now the leaving group, in this case, it started as neutral. It's gaining a pair of electrons. So it's going to be full minus after it's left, so delta minus in the transition state. The carbon that from which the leaving group is departing started completely neutral with a full octet. It's beginning to lose electrons. No extra electrons are coming in to replace the ones it's losing. So it's becoming positive, so it's delta plus on that carbon. Then we have, of course, the product of that first step, which is the carbocation. And now to move the mechanism forward, we think way carbocations behave. Remember we said last time that when you have a carbocation, when you're looking at this carbocation, there's only three things it does, regardless of where it comes from. In this case, it comes from ionization of a carbon-leaving group bond. But regardless of where it comes from, it's always going to do one of three things. Remember what those three things are in no particular order? Capture a nucleophile, be deprotonated, form a pi bond, rearrange. Now, when we're deciding which one operates, all three of them are probably potentially operating. But we have to look at the context we're in and say, which fate gets us to where we need to go? Here's a metaphor. Imagine you're driving down the road. You're going from LA to Burbank because you want to say goodbye to Conan. Hey, if I badmouthed UCLA the way he badmouthed NBC, they'd probably give me $40 million and tell me to leave too. $40 million? Who do I address my comments to? All right, so anyways, imagine you're going to Burbank. So you're driving down the road, you get to an intersection, you go, if I go to the right, I go to Burbank. If I go to the left, I go to Santa Monica. Wow, I really like to go to Santa Monica. Which road do you take? the road that goes to Burbank, because that's where you're trying to get. There are multiple possibilities, but when you're writing a mechanism, pick the pathway that gets you where you are trying to get. The product of the mechanism may not necessarily be the major product of the reaction. It may not be the most energetically favorable pathway, but it's the pathway that you were asked to explain. So here I've told you what the product is, this alcohol. So we have to figure out how do we get there. Which carbocation fate works? What are our possibilities? How about rearrange? Does that look like that's going to get that carbocation to that alcohol? Look where the bond changes are. It's at the same carbon that the leaving group left. The carbon-carbon skeleton remains the same. So rearrangement not likely here. It doesn't look like it's going to be useful. How about be deprotonated to form a pi bond? Do you see a pi bond in the product that wasn't there in the reactants? So that's probably not happening. So that leaves us with capture a nucleophile. What nucleophile should I capture? Yeah, I have basically two nucleophiles that are present, the iodide that left and molecule of water. Molecule of water certainly looks like it's going to get us someplace. Capture a nucleophile. Here is our transition state. Let me draw that down a little bit further. So there's our water coming in, delta plus there, delta plus on that carbon. Product of that we're going to draw in a second. Charges here, delta plus on the carbon because it started as full. It's gaining a pair of electrons from the oxygen, sharing those with the oxygen. It's not giving up any electrons in the process, so a charge is going to go from positive to neutral. The oxygen started as neutral, and it's now sharing electrons and not gaining any back, so it's going to become delta plus in the product of this step. It's going to become fully positive. There is the product of that step. And now to finish up the mechanism, what do I have to do? Look at where we currently are, this oxonium ion. Look at where I went to get to, that alcohol. What do I have to do? This is the beginning of an idea that we'll use a number of times through the course when we figure out mechanisms. It's what I like to call the bond change inventory. See where you currently are, see where you have to get, make an inventory of the changes you have to do, and then figure out how to make them. In this case, we only have to make one bond change, and that is to take away an OH bond. Right? Two OH bonds in this oxonium ion, only one in the product. So we need to take away a hydrogen. What's the name of the thing in a reaction that takes away hydrogens? A base. What base should I use? Hydroxide? Is that a good base? Should I use hydroxide? Can I have $1,000? No. Why not?
I want it.
Correct answer is I don't have any.
Oh, I don't have any.
You don't have any. See? He wants to give me, don't you want to give me $1,000?
Yeah.
But you don't have it, so you can't do it. I would really like to have it, not that I want to take money from you, right? But the point is, he can't give it to me because he doesn't have it. In a mechanism, you can't use things which are not present. Either haven't been specified in the beginning, or you haven't generated as you've gone along. Hydroxide's a wonderful base. It's a strong base. It's not the Arnold Schwarzenegger of bases, but it's not too bad. Strong. I am not right. I'm a base. I'm very strong. Right? No, it's not that kind of base. But regardless of that, it's not present. I can't use it. You can only use what's present. What is the strongest base which is present? Water. You might say I minus because it is a negative charge. It turns out water is a much stronger base. So we're going to use water for the deprotonation. And I'm not going to write the transition state for this. I'll explain why that is in a little bit. There is our product, and it's going to make an H3O plus if you'd like to balance that. All right, so there's our mechanism. It is 3 steps. Ionize of the carbon leaving group bond to form a carbocation. Carbocation does one of its standard carbocation things, in this case capture a molecule of water, capture a nucleophile, and then there is a deprotonation at the end. Now if we're going to talk about this reaction and how changing variables in this reaction, like the leaving group and the nucleophile and so forth, how those might matter, we need to know about the kinetics of the reaction. So let's talk about that. We need to come up with a rate expression. In SN2, it was easy. Most SN2 reactions have one step. Nucleophile reacts with the electrophile, so the kinetics are easy to work out. When the kinetics have more than one step, in this case 3 steps in the mechanism, the rigorous rate expression gets really ugly because you have to add, include elements, facets, for forward and backward for every step in the mechanism. Gets kind of ugly. But as it turns out, it's not that bad. We can see why it's not that bad by working out the energy profile. Like we did for SN2, we're going to draw the energy profile for this. So remember, we plot energy versus the reaction coordinate. And remember, the reaction coordinate simply says this is not time, but rather kind of the progress of one set of molecules from reactants to products. So I'm going to so we have to put a couple of points on here. We have reactants, we have a transition state, we have this guy, we have another transition state, we have this guy, another transition state, which I haven't drawn. Again, I'll explain why, and this guy. So let's start with, I'm going to arbitrarily put the reactants just here. This was the iodide we started with in a molecule of water. I'm just going to arbitrarily give them some energy. And the products I'm going to put over here. Alcohol is the product. Now, although you do not have to know this, the reason this overall process is exothermic, so why the reactants are higher energy than the products, is because a carbon-iodine bond is weaker than a carbon-oxygen bond. That's the fundamental reason. But that's not really important for our discussion here. Now, we have to put, as we go through, this guy has to go on. It's a transition state. Of course, it's higher energy than the reactants. We know that. That's transition state's the highest energy point in the mechanism step. So we'll draw that kind of there. Transition state, and we'll call that transition state number 1. So that corresponds to this. This is number 1. Now, as it comes out of the transition state, the energy goes down. Now we have to begin to ask some relative energy questions. Here we have a carbocation. Is this carbocation going to be higher or lower energy than the transition state that forms it? Lower, because transitions in this mechanism step, that's the highest energy point. Is this carbocation going to be higher or lower in energy than this iodide? Hint. If you have, well, there was a word we used last time. We were trying to come up with ways to explain, to think about the way carbocations behave. And one of the things we said about carbocations is they have a lot of angst is the word I used, right? Anxiety, because they have an open octet and a positive charge. They're not the happiest campers on the earth. As a matter of fact, carbocations are generally so reactive that in most cases you can't put them in a bottle. They exist in a reaction for whatever period of time they exist, fraction of a millisecond, a few seconds, maybe an hour, but they're not the kind of thing you put in a bottle and put in the shelf and say, look, Ma, look what I made in chem lab today. Here's tertiary butyl carbocation. Nope, doesn't work. But it is higher in energy. But it's higher in energy than this. Right? So this, we come out of here, this is our CC for carbocation there. So that's this guy. Now we have to consider this step. We have a transition state, so we're going up in energy again because there's a transition state. There's another transition state, call that TS2. Transition state number 2. Transition state number 2. Now that's going to come out of this, and we now have an oxonium ion, whose energy is certainly less than the carbocation. While the oxonium ion has a positive charge, it doesn't have that open octet. So oxonium ion a little bit more stable. And then the oxonium ion is going to get deprotonated to make the product. Now there's a transition state for this step, but that transition state turns out to be pretty small. Right here is TS, transition state number 3. As it turns out, and this is just one of those things you kind of need to take on faith, it's an empirical observation, proton transfer steps tend to be fast. We know that. And the reason they're fast is because they tend to have low energies of activation. So that's why I've drawn it this way. It's maybe not something you can logic out just from the mechanism, but it's an empirical observation. All right, so that's our overall mechanism. We have 1, 2, 3 transition states because we have a 3-step mechanism. The rate of the overall process depends upon how quickly the ionization occurs, and then the carbocation captures a molecule of water, and then the oxonium ion gets deprotonated. So 3 things have to happen. But one of the things we know about this is that this step is really fast. So if we change the rate of this, it's not going to change the rate of the reaction very much. Between the 2 of these, though, the ionization to make the carbocation, that's my delta G double dagger number 1, versus this step, delta G double dagger number 2, and this is number 3, of course, but that's very small. Between the 2 of these, now you can see I'm going to have the first one bigger than the second one. Did I do that just by accident? No. Did that on purpose. Let's see if we can logic out why that would be. These are energy differences. So we can think about them in terms of bond changes. That's a simplification, but it works pretty well. I mean, remember that since we're talking about delta G has both delta H and delta S components. Remember thermodynamics? But you can, delta H essentially is the bond changes. Delta S is the, very simplistically put, the organization. And as it turns out, the bond changes generally occupy more of the delta G than anything else. So we can approximate this discussion by just talking about bond changes. Here we're throwing away a carbon-iodine bond. Go back and look at this. Ionizing that carbon-iodine bond. We have to pay energy to do that. Are we getting anything in return? No. On the other hand, when the carbocation captures a molecule of water, it's gaining a bond. That's a good thing. Is it paying any bond price? So I have to throw away a bond for the carbocation to capture the molecule of water. Let's go back to that $1,000. Imagine you did have $1,000. Would you give it to me? No, why not? Because you want to keep it, right? If I had $1,000 and you didn't, you'd want it from me, right? Right. So because you want to have the money. If that metaphor doesn't work for you, then let's just talk about the bonds. The molecule would like to have the bonds. It likes to have electrons in pairs, not free-floating in lone pairs. It likes to have full octets. Bonds are better than not bonds. Making a bond is energetically better than breaking a bond. This step is energetically more expensive because you're throwing away a bond. Would you rather be the guy who's giving up the money or the guy who's getting the money? I don't care if it's 3 cents. You'd probably rather be getting the money than giving it away. Same thing here. That is why this step has a bigger energy of activation. It is more energetically expensive to simply throw away the bond. All right, so now what we know is that overall for this process, the rate is going to be mostly dependent upon this first energy of activation because that's the biggest hill. But does it completely control it? Well, here's a way to think about it. This metaphor works especially well today. How many of you, when class is over, get to drive on the 405? All right. So when class is over, you're getting out of class, the first thing you do is you whip open that cell phone and you either call up your friend or tweet your friend or Twitter your friend or whatever it is you do to your friend, and you say, 14D is done, Yahoo, I'm coming home. And your friend comes back and says, great. How long is it going to take? Now you're thinking, I live in, let's say, El Segundo. Anybody here live in El Segundo? Yeah? Okay, so this will work especially well for you, right? Do you take 405 home? You're smart. Let us pretend for the moment that you did take the 405, okay? I'm not saying that you're stupid if you do. Well, you would be kind of on a rainy Friday afternoon. If you're going to go to El Segundo, for those of you who don't know, that's down by LAX. It's essentially a 3-step process to go from campus to El Segundo. There is campus to the 405, 405 to, let's say, El Segundo Boulevard, and then surface streets in El Segundo. So when your friend says, how long does it take you to get home? Do you think, geez, I don't know, 5 minutes to get off of campus. I hope there's no road construction on El Segundo Boulevard because that'll add another 5 minutes. That's not what you think about. You think about, oh my gosh, it's the 405 on a Friday afternoon. I hope there hasn't been an accident. I hope there hasn't been whatever. You think of the 405 because that occupies the majority of your time to get home. If the amount of time it takes you to get off campus is doubled, so what? So now it takes you 3 hours and 5 minutes instead of 3 hours to get home, right? Because if it takes you 5 minutes to get off campus, oh, you've doubled that, it's now 10. If it's the surface treats in El Segundo, oh, that takes you 5 minutes, you double that, that's 10. But that 2.5 hours you spend on the 405, if you double that, that's the thing that's the issue. It is the amount of time that you spend on the 405 which really controls the amount of time it takes for you to get home. That's what this is the equivalent of the 405. This is the slowest step in the process. If I double or half the rate of this, so what? If I double or half the rate of this, doesn't matter as much. This is the big guy. This is the one that controls it. So we call this rate determining step, or sometimes called rate limiting step. And we in here frequently abbreviated as RDS, rate determining step. That's the guy that matters. In many of these kinds of reactions, these other steps are so much faster, that might be 1,000,000 times faster, that this is what you look at when it comes to the rate. Now I'm going to show you something else. For those of you who don't like metaphors, something a little more visual. Like sands through the hourglass, so are the days of our lives. Oh, I said day. How many of you heard me say day? Nobody's going to fess up to it? What, you all deaf? This is a no-win answer, whatever you say, right? Because if you say, yeah, I heard you say day, it's an extra hour you owe me. Right? Days. It was the day in which I said day. All right, never mind. Tough room today. All right, so this is an hourglass. It's a chemistry hourglass made from broken laboratory glassware. Right? These used to be separatory funnels, and this used to be a 1-liter flask. But this is an hourglass. Now, hourglasses, you know, work by having sand to go from one portion into the other, and the rate at which the sand goes from the top to the bottom is a function of the hole that's between the two portions of the hourglass. This guy has 3 areas and 2 holes. This hole right here is a larger diameter than this hole here. Now, what that means is sand moves through this hole faster than it moves through this one. The rate at which the sand moves from one end to the other is a function, of course, of how quickly it moves through the 2 holes. Now, what I'm going to do is turn this thing over and let it go. And in this particular case, the smaller hole is on the top, the larger hole is on the bottom. The sand really isn't spending any time in the middle at all. It's just going right through. In other words, the rate at which the sand goes from the top to the bottom is a function of the little hole. This is the rate determining step in this 2-step mechanism. This is a transition state, this is a transition state, but this one is harder to achieve. The molecules don't do it as quickly. It's higher energy, not as many molecules on average have enough energy to climb over it. All right? So here is a reaction. It produces an intermediate because there's 2 transition states, but as soon as the intermediate's made, it's consumed. Now let me run it in the other direction. This is the same 2-step mechanism, still has an intermediate, but now the slower step is second, and what's happening is you can see all the reactant is now gone, but the intermediate is still there. The reaction's still not done. We're still waiting for this guy. So once again, it's the skinny hole that's controlling the rate. This is still rate determining. The molecules don't go over this hill as quickly. So this is the big hill. All right, so that is our thingy. I'm going to put this away so I don't break it. All right, so now how does the rate determining step work in terms of the overall kinetics? Well, an assumption that we're going to make, and it's usually a reasonably good one, is that the rate determining step occurs so slowly relative to everything else that that's the only thing we have to include in the kinetics expression. In other words, to go back to the 405 metaphor, when you're thinking about going home, you say the rate is really controlled by the 405, and that's it. So same thing here. The rate is just going to be controlled by this. These guys won't enter into it. So our rate expression for this process is constant times. Now, what is involved in this step? That is this transition state right here. So certainly this reactant is involved. The iodide that's being ionized to make the carbocation, that's involved. What else is directly involved in that step? Nothing. The only thing that's in that transition state is this molecule coming apart. That's it. That's all the rate expression is. It says the rate of this reaction is controlled by the concentration of the thing that's being ionized. You will notice that the nucleophile doesn't enter into it at all. So that's our rate expression. So now we're ready to give this mechanism a name. Like SN2, it is a substitution. Like SN2, it is nucleophilic in nature. But unlike SN2, the rate expression, at least in this particular case, is unimolecular. SN2 is bimolecular. It had nucleophile and electrophile. This has just the thing being ionized, so we call this unimolecular. And like SN2, we have an abbreviation, so this becomes SN1. In the old days, when these mechanisms were first being elucidated, they called them SN2 and SN1 based on the kinetics. In a modern sense, we know that SN2 reactions, for example, might be unimolecular if the nucleophile and electrophile are present in the same molecule. So we don't think about them in terms of the kinetics anymore. We now think about them in terms of, is the bond making and bond breaking simultaneous or not? In SN2, it is. In SN1, it is not. It involves a carbocation. So that's how we now think of this. If there is substitution and an sp3 carbon that goes through the carbocation, that's SN1. All right, so there's our rate expression. Now what we can do, one other thing I need to ask to answer at this point. Two things, actually. Number one, this idea that the carbocation forming step is rate determining, this is not the first time we're going to see this. We're going to, 1, 2, 3, at least 3 other cases that I can think of. We may or may not talk about the kinetics, but in those other cases, carbocation formation will also be rate determining. It is a general rule throughout this course, and maybe perhaps through all of organic chemistry. When you have a mechanism that involves a carbocation formation, chances are that carbocation formation is rate determining. So when you're working out kinetics, that's the first place to go. Another question that frequently comes up at this point is, okay, Dr. H, if this is so energetically expensive, if I have to pay this really big price to throw away a bond and make a carbocation, why does it happen at all? I mean, to get back to the $1,000 metaphor, I understand why a person would give away $1,000 because people can be philanthropic. Molecules aren't philanthropic. They could care less about the rest of the world. They don't have any, at least that I'm aware of, any emotions. Maybe they do, and that's a whole nother level. Maybe when it's being ionized, it's going, ah! I don't know. But the question becomes, if this is so energetically expensive, if I'm throwing away that carbon-iodine bond, that's tens of kilocalories. Why would I do that? Well, the molecule doesn't do it because it wants to. It does it because of energy circumstances. Now, the ionization happens because the carbon-iodine bond, or whatever carbon-leaving group bond you have, is vibrating, so it's going out and in and out and in. When it gets to the end of the out cycle, it says, do I go back in or do I simply keep going? If I go back in, the bond stays intact. If I keep going, the bond ionizes. Whether it goes in or out, like a double-double, right, with, cheese and onions, in and out. Am I being unfair? How many of you haven't had lunch? Am I being mean by talking about double-double? Would it be meaner if I added fries and a chocolate shake? Well, let that be a lesson. Have lunch. Anyways, so the question becomes, when it gets to the end of the bond cycle, if the leaving group is good enough, and if the carbocation that would be formed is stable enough, and if there's enough kinetic energy present, it just keeps going. Now, remember, the kinetic energy is related to the temperature of a reaction by an average. Temperature is average kinetic energy. It means if you have a reaction that's at room temperature, some of those molecules are really cold, some of them are really hot. And the ones that are really hot have enough kinetic energy maybe to climb over that hill. But usually not a lot of them. So some of them will be up here and they can climb over easy. A lot of them will be down here and they won't. But if you add energy, if you heat it up, then more of them have enough energy to climb the hill, and so the reaction goes faster. But they can ionize simply because occasionally some of them actually do have enough energy to break that bond. Now, we've talked about our mechanism. Let's talk about variables in this process. Remember, in SN2, we talked about a bunch of different factors. Let's do that in SN1. Now, before you roll your eyes and say, here we go for another 3 hours of lecture, we already know a lot of these kinds of things anyways, because, for example, we've already established what makes a leaving group good, so we don't have to rehash that. So I'm going to compare SN2, to call this SN1 versus SN2, if you like, in terms of a comparison. I know since it's Friday, if you watch professional wrestling, anybody watch professional wrestling on a Friday? Nobody? Good. I mean, that's worse than even some of the reality shows, but hey, but it's fun, right? So this is like a professional wrestling match, SN2 versus SN1. One of the things we talked about was stereochemistry of the process. In a word, how would you define what SN2 does? Inversion. Every single SN2 reaction, regardless of nucleophile, leaving group, etc., always leads to inversion. SN1. What does SN1 do? Well, in SN2, we have to look at the mechanism step in which the geometry of the product is established. That's easy because it's generally only one SN1 step, or SN2 step, excuse me. In SN1, we have three mechanism steps. Ionization to form the carbocation. Carbocation captures the nucleophile, and in this particular case, a deprotonation. I'm going to need to point out, by the way, that not all SN1s have this deprotonation. These two steps, ionize and then capture a nucleophile, every SN1 has those. This is just included because this has an oxoniamide. Which one of these three steps, ionization to make the carbocation, carbocation capturing the nucleophile, or oxoniamide deprotonation, which one of those three steps sets up the geometry of the product? So capture a nucleophile. The deprotonation certainly doesn't change it. This carbon still has 4 things attached around it. This is where it changes, 3 to 4. That's the step we want to look at. So let's figure out what's going on here. We have a carbon, and in this particular case, we have a benzene ring, we have a methyl group, and we have an ethyl group attached. And then we have a p orbital here, 2 lobes of a p orbital. Remember, that's empty. That's where the positive charge is, so to speak. And this structure, the benzene ring, the carbon, the methyl, and the ethyl, that's planar. So we have a plane like so. Now, when the nucleophile comes along, nucleophile, in this case a molecule of water, comes along, it's going to interact with that p orbital to make the new bond. And it can do so by going there, or it can go there. Now, depending upon which face it goes to, let me make this water instead of nucleophile, since that's our actual nucleophile. I don't mean to draw a curved arrow starting at the hydrogen. If you do that on an exam, it'll definitely be a red mark. Because the electrons don't start from the hydrogen, they start from the oxygen. There, maybe that'll be a little more. Okay, so let's draw what the products are. When the water comes in from this face, water, there's the carbon, positive charge on the oxygen. As the water comes in, these groups are going to move away. If there are 3 people sitting on a park bench and the 4th person wants to sit there, assuming you're not New Yorkers, what do? 3 people sitting on a park bench, somebody comes along, and what do? You move away and make space for them. Right? In New York, they go, I got your park bench right here. Right? Any New Yorkers here? New Yorkers? No? No New Yorkers? Really? I can pick on New York City all I want? All right, so there's the benzene ring. There's the methyl group. There is the ethyl group. If the water attacks from this other face, there's the water, there's the carbon, positive charge. And again, the groups move away from the incoming water molecule. Are these 2 products that I've drawn, these 2 carbocation capture nucleophile products, are they identical? All right, first let's ask if they're isomers. Are they isomers? Yes, they have the same formula. Are they, let's figure out what kind of isomers then. Are they constitutional isomers? Do they differ in the sequence in which the atoms are attached? No. Carbon with water, benzene ring, methyl and ethyl. Carbon with water, benzene ring, methyl and ethyl. So they are not constitutional isomers. Are they conformational isomers? Can I convert the molecule on the left by simply rotating around the bond or bonds to make the molecule on the right? And if you work with models, you'll discover that the answer is no. So if they are isomers, but they are not constitutional or conformational, they must be, there's another C word for isomers. If they are not conformational or constitutional, they are, also begins with con. Or there's another common way they're referred to, which doesn't begin with con, doesn't even begin with a C. Well, enantiomers are a group of stereoisomers. The three kinds of isomers that begin with C are constitutional, conformational, and configurational. It's like a prison full of cons. But they're all innocent. So these guys are in fact, stereoisomers, configurational isomers. All right? What kind of stereoisomers? Stereoisomers come in two categories, enantiomers and diastereomers. To be enantiomers, they must be this and this. Two things required for enantiomers. Think back to 14C. Non-superposable mirror images. Are these two guys mirror images? Yes, they are. And you will discover if you play with models, that they are non-superposable. So the guys that I've created here are enantiomers. Now, you might from this conclude, oh, SN1 reactions give mixtures of enantiomers. Be a little careful about that. This particular one does, but there are plenty of examples out there. For example, if there is another stereocenter in the molecule that we don't change in our SN1 reaction, then the products, in fact, are diastereomers, not enantiomers. They might not even be stereoisomers at all. They'll be isomers maybe, or maybe they're identical. So just be really careful when you're referring to the possibilities, whether they're enantiomers, diastereomers, whatever they are. All right, so if they're enantiomers, that means that they have equal energy. Remember, the physical properties of enantiomers only have one difference. It's the direction of rotation of plane polarized light. The energies of the transition states that form them are the same. So this transition state and this transition state have the same energy. If they have the same energy, what do we know about the rate? If reaction A and reaction B both have exactly the same delta G double dagger, their rates are equal. So this suggests from this analysis that this carbocation can be attacked equally from these two faces and give a one-to-one mixture of these. But this drawing is a little bit naive because it's missing a couple of things. One of the things it's missing is a whole bunch of solvent. You don't have to draw all the S's in. It'll make your thing too messy. I'm just using it for an illustration. So there's all these solvent molecules floating around. Now we know that solvent molecules have to move out of the way for things to react. So solvent molecules have to move out of the way for this attack to occur and have to move out of the way for this attack to occur. Well, that doesn't help differentiate between the two faces because the solvent should be the same on either side. That's not a difference. There is something I'm leaving out, though, that is a difference. Go back to this step. What have I not drawn in my little drawing over here? Oh, excuse me, in this step. What have I not drawn in over here that's actually floating around? Yeah, there's some of this floating around. Just because we haven't drawn it doesn't mean it's not there, right? If it's like if you don't open your cell phone bill, that doesn't mean you don't owe the cell phone company money, right? It's there. Now, in SN2 reactions, we left the leaving group out because it usually doesn't matter. But there will be plenty of cases. This is one of them. But there will be plenty of other cases where leaving groups will turn around after they have left and done something else. So if you tend to forget that they're there, draw them in. If you want to leave them out, that's fine, as long as you remember that they're there, because they frequently come back and do something else. I just thought of a metaphor, see if it works. How many of you are familiar with the movie My Super Ex-Girlfriend? Anybody ever see that? Right? So after the girlfriend leaves, and you think she's out the picture, she comes right back. If you haven't seen the movie, especially if you've just recently broken up with someone, this is why you should be careful that the person you've booted out of your relationship isn't a superhero. They will throw sharks at you, among other things. All right. So iodide is in here. Now, relative to the carbocation, there's only one iodide, right? Every carbocation comes from ionization of one carbon-iodine bond. There's lots and lots of solvent, but where is that iodide? Well, it's going to be on one face of the carbocation or the other. Given the way the molecule was drawn, it should be on this side. So I have iodide over here as well. Now, that's the difference between the two faces. The leaving group is partly blocking one face. Not completely, but partly blocking one face and not the other. So what that means is this face, where I have the leaving group leaving, that face is somewhat blocked. That's the face that the leaving group was leaving from. So this backside attack, so to speak, exactly like it was in SN2, the backside of where the carbon leaving group bond was, that side gets favored. So our stereochemistry in this case, we get a mixture of enantiomers, but it's not 1-to-1. 1-to-1? 1-to-1? We get a mixture, but we get mostly inversion and some attack on the same face, retention. Mostly inversion, some retention. Now, what does mostly mean? Is that 99%? Is that 75%? Is that 50.01%? Can't say. It varies from case to case. But SN1s are characterized by having mixture of products, mostly inversion. All right. Another factor we talked about with SN2 reactions was the nature of the nucleophile. In an SN2 reaction, we knew that changing the nucleophile mattered. Making the nucleophile better makes the reaction go faster, but even more fundamentally, we can simply tell from the rate expression that changing the nature of the nucleophile has an impact on the reaction because the nucleophile is involved in the rate expression. Rate equals K times the nucleophile and the electrophile. So this says not only if we change the concentration of the nucleophile, but we change its effectiveness, the rate is going to be influenced. SM1. What about SM1? We can look at the rate expression and make a conclusion from that as well. The rate expression is rate times the same thing I have over there, times the thing that's being ionized. The R group, whatever it is, with the leaving group attached. So judging on that rate expression, if I change the nucleophile in this reaction from water to, pick a good nucleophile, iodide, what would happen to the rate of the reaction? Faster? Iodide's a better nucleophile than water. You think faster? Slower? No effect? I like no effect. This is the step that controls the rate. Yeah, sure. Nucleophile's involved in this step, but this isn't rate determining. This is like leaving campus. This is the 405. You make a change out here, it doesn't matter very much. This is where the changes will significantly affect the rate. Another way to say that is because the nucleophile does not enter into the rate expression. So changing the nucleophile doesn't matter. So nucleophile, who cares? If we improve nucleophilicity, for example, what happens to the rate? Stays the same. Now, it's true that improving the nucleophile will increase the mechanism step where the nucleophile is captured, but generally not to an extent that's really measurable. Now, there is one caveat on this, one warning on this. In SM1 reactions, the nucleophile might also be the solvent, like it is in this case. So if you change the nucleophile, you're actually asking two questions at the same time. What happens to the rate if I change the nucleophile, and what happens to the rate if I change the solvent? So we're going to address that. I don't know if we're going to get to it. Actually, we will get to it today. All right, I'm going to leave my mechanism up here. I think I can erase this. So for SM1, nucleophile doesn't care. Good nucleophile, bad nucleophile, it's the same. Leaving group, that was something else we talked about in SN2 reactions. In SN2, we know that the leaving group matters because it's involved in the rate expression. Once again, write it a different way. Our nucleophile times the thing being substituted. So we know in SN2 reactions, if we have a better leaving group, the reaction goes faster. Another way to think about that is if you think about the rate determining step in an SN2 reaction, is the leaving group involved in the rate determining step of an SN2 reaction? Yes, because the rate determining step is nucleophile attacking the carbon at the same time as the leaving group is leaving. What about in an SN1 reaction? Well, here's our rate expression. Rate equals, told you there was a reason to do the kinetics. Rate equals concentration of thing being ionized. Is the leaving group involved? Yes. In the rate determining step, the leaving group is going away. Okay. So what happens to the rate if I improve the leaving group? What does the rate do? If I improve the leaving group, does the rate go faster, slower, or no significant change? Well, look at the rate determining step here. The leaving group is involved, yes. So if I make this leaving group even more anxious to leave, that makes this process easier. Energy of activation goes down, rate goes up. So improve leaving group, rate improves also. Now you might say, okay, fine, leaving group is involved in SM1, so now we have to think about the nature of leaving groups. We didn't have to think about the nature of nucleophiles here because nucleophiles don't change SM1 rate. As it turns out, we don't have to rethink leaving groups because what makes for a good leaving group makes for a good leaving group. It does not matter whether it's leaving in SN2, SN1, Claisen condensation, Chichi-Bobbin, Fujimoto-Bella, Diels all doesn't have a leaving group in it, but any reaction, a leaving group is a leaving group. They all function the same way. All right. Another variable we talked about was the things attached to the carbon. So the R3 of the electrophile. In SN2 rate, we talked about methyl. Let me just write it this way. Methyl, primary, secondary, tertiary in terms of rate. Little review here. When the leaving group is attached to a methyl carbon, everything else being equal, does that make our is that slower or faster than when the leaving group is attached to a primary carbon in an SN2 reaction? Right, faster. Primary faster than secondary, secondary much faster than tertiary, so much that we say tertiary is NR. Reasoning? Steric hindrance. The more crowded you make the carbon that bears the leaving group, the more energy it costs to bring the nucleophile in because there's more repulsion. More energy means slower rate. What about SN1 rate? Let's make the same argument. Methyl bearing the leaving group, primary carbon, secondary carbon, tertiary carbon. To answer that question, we go to our rate determining step, transition state, right there. Is steric hindrance an cation? Nucleophiles not coming in. What is happening? What's happening is that this carbon is beginning to build up a charge. It's beginning to become carbocation-like. What happens to the stability of a carbocation, and consequently its ease of being made, when we increase the number of alkyl groups? In other words, is it easier to make a methyl carbocation or a primary carbocation? It's easier to make primary. Primary is more stable. So the rate for methyl is slower, and so on. Tertiary, SN1 reactions at tertiary carbons are fastest because the carbocation, that's the thing we're making in the rate determining step, is most stable. More stable carbocation means lower energy of activation because the carbon in the transition state up here can deal with its delta plus a little bit better. Methyl carbocations, CH3 plus carbocations, I'm not talking about methyl with resonance. Methyl carbocations are so unhappy, are so terribly difficult to make. CH3 plus, we will never ever invoke CH3 plus. Primary, you better have a good reason. More stable than primary, knock yourself out, you can do it all you want. Now, there's one more variable left which I will leave for you to think about over the weekend. That is solvent effects. What kind of solvent do I want for an SN1 reaction? Polar, nonpolar, protic, aprotic. Think about it over the weekend. See you Monday.